Hi, everyone. Like Diana was saying, today we're going to talk a little bit more about physically realizing qubits. We've talked a lot about theory, but at the end of the day, we need to take that theory and make it a reality. And how do we do that? We need to make that information physical. We need to have a physical means to encode this information. So think about classically how we have voltage or current in a wire, something that is like actually a charge, like a charge within a battery. So that information will be something that is physical. So we need to take all these concepts we've learned for quantum computing and tie it to something real so we can actually compute. So today we're going to talk a little bit about the physical realizations of qubits. First, some of the guidelines we need to follow in order to physically realize qubits, as well as some example implementation. So pretty exciting stuff. So if anyone has any questions, just feel free to stop me. So building quantum systems. We have a logical qubit. We've done lots of work with logical qubits, but we need to take that and encode that into an actual device, whether that is an ion within a trap or a superconducting circuit within a refrigerator. So we have all these properties associated with quantum information science, but how do we realize those systems? How do we realize these very intricate details about quantum computing that involve phase, that involve entanglement, that involve superposition? We need to have all those abilities for a qubit. We need to be able to physically realize them in some way. So we like to differentiate between the logical qubit. So the logical qubit is the information that we have described in an algorithm. So we had our quantum circuits with our gates. We would call those logical qubits, and we have to map them to physical qubits. So today in our devices, they're very new still. We're working on developing them, making them better. But as of now, we have a one-to-one mapping of logical algorithm qubit to a physical device qubit. As we move into more complex and more robust devices, we're going to start having these corrective codes that we'll use that will be able to take a logical qubit and encode them into many physical qubits. But for today, we're just really going to focus on looking at taking a one-to-one mapping with logical qubit and immediately implementing it as a physical qubit on a device. So we have to have a way to encode those logical algorithm qubits into physical device qubits. And just something to note, so these pictures are from the Stack Lab, and this is from actually the Schuster Lab at UChicago. So some real devices that are actively being used for research. So the physical implementation of quantum computation, what does that mean? So these are a set of rules that were outlined in 2000. So the paper is linked here. We can also make sure that the paper is linked so everyone can take a look. It's not too difficult of a read, but it's one that is commonly looked at in quantum information science because it outlines, and remember, this is in 2000, before we really even had very many quantum devices. So this paper outlines what the requirements are for a quantum computer to realize quantum computation, and is outlined by David DiVenzo. So a couple of these criteria, so there's 5, and then an additional 2 for communication. So number 1 is that a scalable physical system has to have well-characterized qubits. So all of those physical qubits that today are realizing logical qubits, they need to be able to be differentiated, so you can tell one qubit from another, and you can be able to interact with those qubits independently. So criteria number 2, the ability to initialize the state of the qubits. So for example, the ground state or the state of all 0. So we have to be able to faithfully be able to start up our system and start it up to a known state. We don't want to start our computation with some random values because that would just give us a bunch of noise at the end of the day. So we need to start in some known state, and oftentimes, just because it's easier, we oftentimes start with the ground state of all 0. So we oftentimes call the logical encoding, our quantum register for our qubits, and that will start in 0 before we act on it to put it into superposition, entanglement, whatever our algorithm requires. Criteria number 3, long relevant decoherence times, much longer than the gate operation time. So we'll talk a bit about this in more depth in a couple of slides, but we basically want to make sure that not only are we able to realize a qubit, initialize it, we want to make sure that it's going to be good for computation for a reasonable amount of time. If we have a qubit that's only useful for maybe a couple of computation cycles, that doesn't allow us to implement very many algorithms of much depth. So it's important to have long decoherence times, or times that you're able to actually implement computation, so that we can implement meaningful qubit transformations and therefore meaningful computations. Next, we have to have a universal set of quantum gates. So what does that mean? In just a high-level view, a universal set of gates, we won't really worry about getting into the details, but that means that we have gates that can implement quantum algorithms. And 5, qubit-specific measurement capability. So we want to make sure that we can have these qubits that are well-defined, we can have them independent from each other so we can operate on them, and we want to make sure that we can interact with them not only to evolve their state, but to measure that state. So these are our 5 criteria that were outlined by David DiVenzo in 2000, and we're going to dive into a little bit more depth for each one of these before actually looking at a couple of example physical implementations of qubits. So first, let's look at scalable quantum systems. So we want to make sure that we have clear qubit states of ket 0, ket 1, so our computational basis, and the ability to move into superpositions of those two states. So we have to obey the fact that we have the absolute value squared of alpha plus the absolute value squared of beta. That must be equal to 1, just because we have to have a total of 100% probability that we're either in state 0 or 1. So we need to obey this criteria. And then also we have to have the ability for qubits to become entangled. Entanglement is one of those really important features of quantum computing, one of those that allow us to have a little bit more of an advantage with some tasks as compared to quantum compute, or as compared to classical computing. So if we are not able to entangle our qubits, we lose a lot of that power associated with quantum informatics. So we want to not only be able to have the ability to move between superpositions, we want to make sure that we can take these qubits and interact them in such a way so that they become entangled. Next, although we don't have to have the ability for each qubit to be able to talk to each other, we need to be able to communicate in some way. So sometimes that's used with a swap gate. With some of these devices, they are constructed in such a way that they are physically stuck to where they are on that chip. So for example, look at superconducting circuits. We might not be able to actually move the qubits, but we can use that swap operation to logically swap the information of 2 qubits. So we need to make sure that we have a way to communicate across the chip, even if each qubit cannot directly talk to every other qubit with a physical connection. So oftentimes the swap operation helps us out in that case. So let's look at the layout for IBM Yorktown. So this is a quantum device that you will actually be able to play with whenever we go into the next couple of weeks, where we start experimenting with the IBM quantum experience. And this is the layout. So layout is essentially just how the qubits are configured on the chip. So we can see that qubit 0 and qubit 1 have a physical connection. Qubit 0, qubit 2 have a physical connection, but qubit 0 and qubit 3 do not. But that's okay. We still are able to satisfy those requirements for quantum computation simply because we have that swap operation that we've worked with so many times. We're able to swap the information from qubit 0 to qubit 2, then qubit 2 to qubit 3, in order to move around the chip so that we can have qubits that are not physically adjacent to each other be able to interact for computation. Next, we have to have the ability to grow these systems over time. There shouldn't be something about the system that causes the error to scale exponentially to make it difficult to realize a large-scale quantum computation with that sort of platform. So we want to make sure that with these devices we're investigating and all these candidate platforms for quantum computing, that there's nothing intrinsically wrong with the physical setup, so that it's simply just too difficult to manufacture bigger devices in the future. So what kind of things do we have to consider with those physical devices? We want to make sure that those errors associated with the device or engineering costs, we don't want the design of a chip, if we want to scale from 5 to 5,000, to be so difficult to engineer that it's just simply not worth the benefits you would get from that device. So we want to make sure that whenever we are thinking about what devices we want to use for quantum computation, we don't want the engineering costs or the errors associated with it to scale exponentially as we increase the number of qubits. So all of these different things are things we have to think about when we move into scalable quantum systems. All right, let's talk about initializing those qubits. So we need to start our qubits at some known value before we can move them into superposition, before we can move them into entanglement, before we can have them interact in any sort of algorithmic way. Oftentimes we use the ground state. So when I say ground state, I just mean the state of Ket 0. This is usually chosen because it's simply easier than to go to a Ket 1 or an excited state. So what happens if you needed a Ket 1 for your computation? So let's say you are working with an algorithm, you want to put yourself into the superposition state with phase. Well, you need to do that with a Hadamard operation after you're in a Ket 1. So if you need that Ket 1, a NOT gate is applied before further processing. So let's look at this. So here we have a quantum circuit. We have to start in our ground state, but we want a couple of these qubits to be initialized to Ket 1. So we're just going to put a couple of NOT gates down there. And as our qubits evolve over time, we have now qubits that have a value of Ket 1. So this is how you would take your starting state, even though you are starting in a ground state, you can easily evolve it to get whatever known state you would want after that. So initializing qubits is a very important aspect of these scalable quantum systems and to implement your quantum computers. So long coherence times. This one, you can really start diving deep into the details, but we'll just kind of stay at the surface level for now. With qubits, we talked about how they're very sensitive, they like to interact, and they unintentionally interact with, in most cases, they like to interact. And most times, if we're not careful, they can unintentionally interact with each other and with their environment. So we have this concept of decoherence, which causes a qubit to move from its desired state. So for example, we initialized it to a ground state. We passed the qubits through a couple of NOT gates to get a couple of the qubits into a state Ket 1. But if we just leave these qubits to their own devices, they're eventually going to want to move away from this known state to something we don't know. And that's not ideal in computation. We don't want to send inputs into a quantum circuit that we don't know, because that's going to just generate an output that we don't know. So if too much decoherence adds up, it just compounds over time and the state becomes useless. Our computation becomes useless just because you send an unknown into a circuit, you're going to most likely get unknown outputs. So we have to have qubit states stable enough for a long enough period of time that when operations are implemented, you get something meaningful out. So we have this term called coherence time. Sometimes it's called decoherence time, but it's basically the same thing, where it's the duration of time that it's used for quantum computation. So coherence time should be much longer, ideally, than gate time, so that you can get many, many gates inside of that coherence window, so that you can produce outputs that are meaningful and be able to measure those meaningful outputs at the end of your computation. So let's look at some examples of decoherence. These are just some key ones of Ket 1 fading into Ket 0, or we have a superposition state fading into a superposition state with phase, or eventually evolving into either Ket 1 or Ket 0, so losing that superposition entirely. These are extreme cases, but decoherence can be slight as well. So even slight tuning of that state, a slight tuning of that superposition is, and oftentimes, not what we want. We don't want that to pass through our algorithms, because that could cause unintended consequences in the sense that we get an output from that algorithm that's not what we desire. So let's look at that IBM Yorktown device again, and we can see that there's some differences across this device. Even though all of these qubits are on the same chip, they do not have the same coherence times. And that's something that's very important, and something that's one thing that we're working to improve during this current era of physical quantum devices. So here we are looking at T1 coherence times. There's a couple of different types of coherence times, but we'll just look at T1. If we look at a NOT gate time, so a NOT gate time is 0.035 microseconds, and we look at the coherence times for these qubits, we can see that the coherence time for qubit 1 is almost double that of, well, maybe not double, but it's significantly more than qubit 2. So if we took this coherence time divided by the gate time, we would get approximately 1,700 operations on qubit 1 before we decohere, and only about 1,100 on qubit 2 before we decohere. So that's a significant difference. That's almost double the amount of gates on qubit 1 as compared to qubit 2. So it's very important to highlight that we have to take the real abilities of these current devices into consideration when we're executing algorithms, because even on the chip, we have some qubits that perform better in some ways than others. So that you do see a lot of variation in current devices, but that is something that engineers and scientists are working to improve. And we also are working with computer scientists and to be able to improve mapping algorithms that make the best use of these devices. The next requirement is a universal set of gates. So whenever we look at a universal set of gates, that basically means that we should be able to implement every quantum algorithm we want to on the device. So we call that a complete set of gates. So complete enough to build arbitrary algorithms for execution on that device. So what does that mean exactly? Well, we can't implement useful circuits on just NOT and CNOT alone. Why is that? Well, with just NOT and CNOT, as we've already seen in class, we can do some cool stuff, but we are not able to generate entanglement. We're not able to generate superposition. So you need those additional operations that give quantum computing its power. And that power comes from superposition, interactions of phases, and entanglement. So we want to make sure that we have enough gates that make our computations robust. So very, very important. One kind of cool aspect that we'll talk a little bit about in the coming weeks is the fact that we might have these really complicated gates we need to implement, but these can be constructed from smaller, simpler ones. So let's say we have this really complex 4-qubit circuit, and we don't really have a direct way to physically implement this on qubits, but luckily we're able to take that and decompose it into a nice, happy set of gates that can actually be physically implemented efficiently on a particular platform. So this universal set of gates is often a set of single qubit gates with a 2-qubit operator, and with those gates you can approximate any arbitrary algorithm that you want or would need to execute on a quantum device. Next, we have to have a measurement capability. So we must be able to output one of two possible states. So we might be in a superposition of Ket 0 and Ket 1, but we need to be able to measure one of those two states and have that be our final output for our evaluation of that circuit. So once again, upon measurement, we lose all of those quantum properties of that state with superposition, and we collapse just to a classical value of 0 or 1. So something very important to remember. So measurement needs to be able to accurately reflect that current value of that quantum state. And it shouldn't bias it in one way or another. So what does that mean exactly? So let's take a state that's in perfect superposition. So if we look at the probability of observing either ket 0 and ket 1 for this state psi, we take the magnitude squared of each of the probability amplitudes. We know the probability amplitudes here are 1 over square root of 2. We know that 1 over square root of 2 squared is going to be 1/2. So we should get a 1/2 chance of observing a ket 0 and a 1/2 chance of observing a ket 1. So if we run this algorithm that produced this quantum state on our quantum device, and we measured it 1,000 times, what would we expect to get? We would expect to get a 50-50 split between measuring 0 and measuring 1 if we had a measurement capability that was accurately reflecting the state of the qubit without any sort of bias. So in a perfect ideal machine, we would get a result of 500 measurements of 0 and 500 measurements resulting in 1. Of course, we're working with devices that aren't exactly perfect. So measurement error, gate error, other additional noises prevent us from observing a perfect 50-50 split, but we are working towards building devices that can observe the state of the qubit as accurately as possible. So if we were working with an ideal device, this state here would collapse into either 0 or 1 with even chance. So now we're going to talk about some example qubit technology. Before I start this part, are there any questions? Okay. All right, so we'll go ahead and start diving into different types of qubit technology. So today we're going to talk about 3. So we'll talk about superconducting circuits, trapped ions, and photons. So with these physical devices, we're going to be able to realize a qubit. And as a note, whenever we look at trapped ions and photons, those would be an example of a microscopic qubit, whereas superconducting circuits are macroscopic in the sense that they're a little bit larger. Here we're working with particles, and with superconducting circuits, we're looking at a system that acts as a qubit. So we'll start looking at superconducting qubits. So we have a qubit realized as a circuit, and the energy is encoded with different circuit energy levels or charges. Now, as a note, there are different types of superconducting circuits. Some use flux and phase, but here we're working with charge-based qubits. So we are looking at differences in energy levels or charges. So in these superconducting circuits that have many qubits on them, we have these qubits connected together with resonators, often in a grid pattern. So we talked about that whole communication issue. We need to have qubits be able to communicate with each other to implement operations. And oftentimes they aren't fully connected in a full mesh topology. So these qubits, even though they aren't fully connected, as we saw with the IBM Yorktown device, they can implement swap operations to enable communication between those qubits. But oftentimes, these devices are arranged in a grid pattern so that there's as much connections with the locally adjacent qubits as possible. We call these kind of a nearest neighbor topology as a side note. So in these superconducting devices, we have devices that have 50+ qubits. And these devices must be cooled to extremely low temperatures, so cryogenic temperatures, very close to 0 Kelvin, in order to remove any external sources of any external sources of energy. So one of the things that's kind of a cool little fact is that inside of these quantum computers, so these quantum computers are housed oftentimes in these giant refrigerators that have to keep them super cooled. So we want to limit that decoherence, that interaction with the external world. So we want to have that system chilled so that all of the external energy is near zero. We don't want to have any external energy around that system. So because these systems are super chilled, some of the coldest places on the universe are within these quantum refrigerators that are holding these quantum systems. So that's kind of cool. So with these superconducting qubits, we have quantum operations that are realized when microwave signals are targeted at those qubits. So we have a qubit, and we not only need to have a way to measure it, we need to have a way to actually be able to implement operations. So these quantum operations are realized with microwave signals. So we just point a microwave signal at that qubit's resonator and use it to evolve it into different qubit states. So here we have a picture of the Schuster Lab superconducting qubit device. And here we have an actual picture of the IBM Q Yorktown device, which is pretty cool. So just as a note, we have a couple of different things that are fun to point out with this device. So we have our qubits labeled with Qs. We have resonators that connect qubits, so these allow us to communicate with the qubits. And each one of these qubits also has its own independent resonator. So these resonators essentially these resonators allow us to have control and readout capabilities for each of these qubits. So we want to be able to evolve it with, we apply some microwave signals to evolve the qubit state, and then we apply other signals in order to cause a measurement, and then that causes an output for that particular qubit. So here we can apply a signal for qubit control, and then we have our qubit communication allowed with this connection right here. So this connection, we also call it a resonator. All right, now let's talk about some trapped ions. So here we have a picture of the trapped ion chip from the STACK lab. And with a trapped ion device, we realize our qubits as ions. So we have 0 and 1, or Ket0 and Ket1, encoded with stable electronic states of the ion. So we have these electronic states associated with the ion, that allows us to encode our basis states of 0 and or Ket0 and Ket1. So there's a bunch of different types of qubits that can be realized, or a bunch of different types of ions that you can use to realize these systems, and they just have different properties depending on like what you're looking for your quantum device. That's just an interesting aside. So another note about trapped ion devices: the ions within those trapped ion devices can be moved around between traps, and they also are capable of long interaction range. So ions within a trap don't need to be next to each other to interact. So that's one characteristic that a lot of people would say is a benefit of trapped ion devices, is the fact that whenever we're looking at interactions or operations between two qubits realized as ions, they don't have to be adjacent in order to interact. Unlike when we're looking at a superconducting device that has a nearest neighbor topology, if we want to have a two qubit operation implemented, those two qubits need to be adjacent in order for our qubits to be able to interact. So you have to implement swap operations to get those two qubits adjacent to each other before we're able to actually implement the two qubit operation of interest. ions have long coherence times. So we looked at the coherence times of the superconducting device, the IBM Q Yorktown, what it was reporting in February. And you can just go in on the IBM Quantum Experience and check out the coherence times for devices. But for ions, so for the IBM device, that the coherence time was about in the range of tens of microseconds. For the trapped ion devices, we can have really long coherence times, and you can particularly, or you can choose particular ions for your device so that you have longer coherence time. So the ion you choose for your implementation influences how long your coherence time is. But they've been demonstrated to have coherence times that are in the seconds plus time frame. So systems with tens of qubits exist for the trapped ion types of devices. And once again, so they don't interact with their external environment. We don't want the qubits encoded as ions to decohere. These systems also need to be cooled to extremely low temperatures in order to remove all external sources of energy. So just like with the superconducting devices, we need to make sure that these devices are also housed in a cryogenic refrigerator. Whenever we implement quantum operations with trapped ions, those are implemented by applying laser pulses to the ions. So now we're going to look at a little bit of a cartoon of a trapped ion. So here we have a 5-qubit trapped ion machine. And if we look at what the system consists of, we have electrodes that are actively trapping those ions. We have the ions that are being used for quantum computing. They kind of move around, so they move around because their energy levels are changing to be able to evolve quantum state. And then we control them with laser light, so that allows implementations of gate operations. And then there's also special procedures to allow for the readout of those quantum states. So once again, ions have the ability to have long interaction ranges between qubits within the trap. And then we also can move qubits around between traps and shuttle them around so that we have even more connectivity between ions in a trapped ion system. So photonic qubits. These are a very interesting type of qubit simply because there are many different ways that you can realize a photonic quantum computer. So these are just a couple of different techniques. There are actually a few more, but we're going to look at polarization, space, and frequency. There's also orbital angular momentum, time bins. There's a lot of different ways that you can encode photonic quantum information, but we're just going to focus on the information in this table here. Start with polarization. The way that you would encode information typically in the literature would be that horizontal polarization would be your ket 0 and vertical polarization would be your ket 1. So if we look at this cartoon here, we would have a vertically polarized light that would be encoding a ket 1, and horizontal polarized light would be encoding ket 0. So how does that work exactly? So if you have a photon that is encoding a qubit, if it has a vertical polarization, that qubit has a value of ket 1, and if it's horizontally polarized, that qubit would have a value of ket 0. If it's in superposition, you don't know if it's polarized, if it's either in a horizontal or vertical polarization. Upon measurement, you would see if it's polarized either horizontally or vertically. Another way to encode quantum information in a photonic system would be with space. So spatially encoding quantum information oftentimes just is, where is your information located? Where is your photon that is encoding a qubit? Where is it located? So typically, if you look at papers that use rail encoding, so that's another term for it, rail encoding, you would have the top rail be your ket 0 and your bottom rail be your ket 1. So just where your qubit is located, and you determine that upon measurement, where that photon is the value of the qubit in a given moment of time. Finally, we have frequency. So frequency assigns one frequency value for one basis state. So ket 0 could be frequency F, and then frequency for 1 would be, or ket 1 would be frequency plus some delta, so some change. So if we think about what that would look like visually, we would have one frequency for ket 0. And as we increase our frequency, that causes a signal to oscillate faster. So if we add a delta to our frequency to create state ket 1, we're going to have a slightly faster oscillation. So when we measure this photon, the frequency at which it is traveling is going to be its particular value, so either ket 0 or ket 1. And as we talked about with the Divinzo criteria, we have to be able to, in all these systems, not only have clearly defined basis states, but be able to be in superposition of those basis states. So we have the ability to be in superposition of polarization, of location in space, and of frequency. So because of that, we're able to realize quantum information in these different encoding mechanisms. So let's look a little bit more in depth at photonic qubits. So photons resist decoherence, and they retain a quantum state for long periods of time at room temperature. So because of that, photons are very, they're looked on favorably for those reasons, because they're so resistant to decoherence. They don't want to interact with their environment. And unlike other quantum systems that are, that must be super chilled, so think about those superconducting circuits, think about those trapped ions, those systems need to be kept very, very cold in order to work. But photonic quantum systems don't need to be kept cold. In fact, there have been quantum photonic demonstrations that are just on a tabletop at room temperature. So these systems don't need to have any sort of requirements with respect to the temperature of their operation or their operating environment, which is very exciting. So because of that, because they're able to be very stable at room temperature, they're projected to be used as flying or communication qubits. So they will be able to maintain their coherence for long periods of time, and they can be transmitted at room temperature. So that's really great. And because of that, they're projected to be used for communication, which is nice because we already have a lot of infrastructure classically for photonic communication. So the hope is that some of those ideas can be borrowed from in order to build up the infrastructure that would be needed for networks of photonic interconnects, so that qubits could travel from point A to point B. So unfortunately, this strength, this positive attribute that photons resist decoherence also ends up being a caveat, because photons not only want to resist interaction with their environment, they want to resist interacting with each other. So because photons resist interactions with each other, multi-qubit gates are very challenging, and that's one of the biggest limiting factors in why you don't see more photonic quantum implementations. If we want to get into more of the details, if you want to implement photonic gates with linear photonics, so linear photonics are elements like beam splitters, wave plates, etc. These interactions are probabilistic because these photons don't want to interact. They only interact sometimes. So there's an associated probability with some quantum photonic implementations of how they will interact and whether or not they will interact. So because photons don't really want to interact with other elements in their environment, they resist interacting with each other, and 2-qubit gates are challenging. And going back to that criteria of being able to have qubits have a universal set of gates, one of the requirements is that you have to have at least one gate that allows interaction between qubits. So this is a big limiting factor in making photonic qubits a scalable means of quantum computation. But it still has a lot of benefits and is still very much projected to be used as a communication mechanism in quantum systems for qubit information. So how do we realize operations with photonic qubits? Photonic or quantum photonic operations can be implemented with elements such as lenses, mirrors, wave plates, phase shifters, beam splitters. So those linear optic elements, those are examples of them. So those are able to be implemented in a way that are able to evolve that qubit quantum state. And it's able to evolve quite easily. So unlike other quantum systems that have high errors associated with their gate implementations, whenever we're talking about single qubit operations on photonic qubits, they're able to be implemented very, very well because we are using these devices. So you're able to very reliably evolve single qubit state when you're thinking about quantum photonics. So let's look at some examples, or just 2 examples of implementations. So these are schematics of Z gates. So Z gate, once again, is our phase flip gate. And if we have a qubit state going in this dual rail implementation, so dual rail from the past slide, if we have our top qubit, if our photon is in the top rail, it's in a state cat 0. If it's in the bottom rail, we're in a state cat 1. What do we know about our phase flip or Z gate? Well, it only acts on the qubit cat 1 element. So if we're in state cat 0, we have no observed phase change. But if we're in state cat 1, we have a phase shift. So here we have a phase shifter that acts on that bottom rail in order to cause a phase shift if we're in the cat 1 state for the qubit. And that shift is, of course, a shift of pi, or 180 degrees. So for photonic polarization, Z gate, so this implementation, we have our qubit state implemented as a polarization of that photon. So we can go back and see that if we have a horizontal polarization, cat 0, vertical polarization, cat 1. So we build this structure so that with this beam splitter, so polarized beam splitter, we pass the photon through. And if we're in a state cat 1, we go ahead and go to the bottom rail. And if we're in state cat 0, we stay on this top rail. So we won't really worry about too much of the details of this implementation because there's a couple of different moving parts here. But whenever we're in the top rail, we do not incur a phase shift on our quantum information. But in the bottom rail, and if we are in state cat 1, we have our Z gate implemented. So that phase shift where we start seeing that negative sign associated with the cat 1 on our quantum state. So looking towards the future, so we talked about the Divenzo criteria for scalable quantum systems, what we need to implement a quantum computer, and there's some additional information that he included in his original write-up. So in this write-up, he had 5 criteria for quantum systems, and then an additional 2 that outline what is necessary for quantum communication. So just as a note, we're still working on creating robust quantum systems that can faithfully implement those 5 criteria. But these are things that need to be considered as we work towards moving away from single quantum systems and moving into a space where we have multiple quantum systems that are connected together, like you would see in distributed systems today, how we have multiple compute units communicating together and kind of acting as one. So the requirements for quantum communication are as follows. So one, we need to have these stationary and flying qubits. So stationary being our compute qubits, flying being our communication qubits. They must be able to interact, and they must be able to interact with high probability and in a robust manner. So we don't want to lose the information that we just computed in order to allow it to be transmitted to another location. And two, flying qubits must be able to be transmitted at high quality. So these flying qubits, not only do they need to be able to interact with our compute qubits, they must be able to interact with those compute qubits and take information from point A to point B with high fidelity. So what does that mean? So let's think about if we have a qubit, we know that qubits have to be able to demonstrate the ability to be in superposition, to interact with their phase, for constructive and destructive interference, to be entangled. So if we have any of these properties with the qubits, we want to make sure that superposition, that entanglement, all of that phase information, we want to make sure that is preserved when we're going from compute to communication qubits, and while those communication qubits are being transmitted from point A to point B. So very, very important. As we build up our quantum systems, we'll eventually move into the space where we'll have networks of nodes. So we need to make sure that we keep these requirements in mind as we move to those networks of nodes. So to summarize, we have a lot of different rules that define quantum computing. We talked about the theory in class of what a qubit is, what a quantum operation is, how we make a quantum algorithm, but we have to take that logical information and put it into a physical encoding. So there's a lot of different rules for doing that, and those rules, they influence how we physically realize qubit state, how we realize qubit operations, and how we implement quantum communication. So for computation to occur, logical qubits and operations must be encoded into a physical technology that can support quantum properties. So that's critical. It's really, really important. Information at the end of the day is physical, so we have to make sure that we can take those logical qubits and realize them on an actual platform. So we talked about superconducting circuits, we talked about ions, and we talked about photons. And those are just a few. There are many different contenders for a quantum computer, or there's many different competing platforms that have their strengths and weaknesses. And at this point, it's really unclear which one will become the standard for quantum computation. And it'll be exciting to see in the coming years which platforms will be able to follow the criteria that have been outlined and become the standard platform, much like how transistors have become the standard platform for classical computation. So I'm sure that it'll become a bit more clear in the coming years, or we'll reach this kind of agreement that some types of quantum computers are better at implementing some types of computation, where others are better at implementing others. So very, very interesting to think about. So with that, are there any questions for